Thanks, Hal and Ignacio, and to all the organizers for putting this event together. Based on the attendees that I've seen, it looks like we have many of the thought leaders in the space of machine programming, what I like to call it. And so I'm actually really excited about what we are likely to discover and discuss over the next 2 days. The focus of this talk will be on the challenges and opportunities in MP. And as Hal mentioned, for those of you who don't know me, which is probably not too many of you, I basically try to drive and oversee the research agenda for machine programming across Intel. And we're also taking that research and investigating ways that we can apply it directly to Intel's processes with Intel partners and actually into products. So it's evolving very quickly into more than just the research space. As you can see, I really love to collaborate with people. This is certainly an incomplete list of my active collaborators. I apologize if I'm collaborating with you and you're on the line and your name is overlooked. Please just let me know and I'll update this list. For today's talk, my plan was to cover 9 different areas. Unfortunately, after I put this talk together, I realized that's a bit too aggressive and the talk would probably move at a rate that would be a little bit confusing. So instead of 9 topics, I'm just going to focus on 6. And I'll quickly discuss the 3 that I had to skip at the very end. And we don't need to go through this entire list of 9 topics. As I switch to the next topic, you'll see a slide like this that'll highlight what I'm about to talk about. So for this first topic, I'm going to talk about machine programming using approximate and precise methods. But before I do that, I'd like to provide a little background. As most of you know, many of my machine programming talks start with a slide on the 3 pillars of machine programming. This paper is a joint work of Intel Labs and MIT that we published in 2018 at MAPL, the Machine Learning and Programming Languages Workshop that we put together around 2016. The 3 pillars of machine programming focus on what we believe are the core conceptual areas of MP, those being intention, invention, and adaptation. Just to briefly summarize each of these pillars, what intention is aiming to do is help us come up with non-traditional ways, allowing humans to provide and express their ideas to the machine that will make them more productive. And what the sort of the primary impetus behind the intention pillar is that we believe general purpose programming today is becoming overly complex, and without a very specific focus on intentionality, we think this problem will quickly run away from us. In addition to creating new types of techniques of intention, such as natural language, physical gestures, visual diagrams, things of that nature, intention is also aimed at helping us extract out the meaning behind programs. And then when we have those things, hopefully we'll be able to improve programmer productivity. Once we move from the intention pillar, we hope to build what we call these inventive systems that basically are designed to implement at a very high level what was expressed as the intention. And this essentially consists of the data structures and the algorithms for that program. Even though the pillar is called invention, much of the ideas behind the invention pillar are simply combining things that already exist to satisfy essentially the requirements or the specification of that user's intention. However, there are certain cases where actual invention will happen in the invention pillar. And I'll show you a couple examples of that later in this talk. Once that high-level program has been invented, we then pivot to the adaptation pillar, which is meant to do the fine-tuning of the program so it works in a particular software and hardware ecosystem. One could imagine that if you are writing a sort function that's going to run on your mobile device, that's going to process maybe a couple kilobytes of data, that algorithm might look very different than a sort algorithm that's going to run on a cluster of machines in the cloud that's going to be sorting petabytes of data. And this is really what the adaptation pillar is about. In addition, as we all know, software continues to evolve, and what we want the adaptation pillar to do is be able to, toward the end where we reach full automation, be able to automatically in a closed loop system adapt that software as things around it evolve. So the software stays correct, efficient, secure, and all the other quality metrics that we might want to measure it by. Now that we have an understanding of the three pillars of machine programming, I want to take just one quick moment to talk a little bit about machine programming itself. The sort of abbreviated definition of MP is about the automation of software development. But why did we choose the term machine programming? Did we do this to confuse people? Did we do this to try to coin some new term and put us on the map? Actually, the reason why we did this is as we were putting this paper together, we looked at some of the alternatives that we could have chosen, and each of these terms seemed to have some sort of connotation that wasn't representative of what we were trying to achieve. For example, historically, program synthesis has been bound to formal methods. I don't think that that's necessarily the case today, but historically, we think that there may be a conceptual mindset that that is what is in program synthesis. On the other hand, AI or ML for code makes it very clear that the techniques will only be artificial intelligence and machine learning, and we clearly don't want to just do that. And then lastly, we have this term software 2.0, which I still don't quite understand what it means. I believe that Andrej Karpathy's original blog post says that it's meant to have neural networks be a replacement for all code. And if that's the case, I think that definition is pretty narrow, and we certainly don't want to do that. I also think that the term software 2.0 doesn't necessarily imply anything from its name. And then on top of that, I don't know what 3.0, 4.0, and 5.0 might look like. So our goal with the term machine programming was actually to avoid confusion and broaden the scope. And this is sort of the history of why we chose this term. So now that we have all that clarified, we can dive into our first topic, which is machine programming using these, what I call approximate and precise methods. So when I think about MP, I generally consider it using two primary areas. This, of course, is not meant to be exhaustive, and machine learning and formal methods are only one representation of those approximate and precise techniques. But what I find is that in different scenarios, you may need different types of solutions. And in some emerging work, what we're starting to see is a fusion of both. In particular, I'd like to point our attention to two of these works that have just come out recently. The first is this learning to infer program sketches, which is an extension of Armando's prior work, which, as Hal had mentioned in his introduction, sketching is really about kind of filling these holes automatically. And what Armando and his team have done is basically extend the concept of sketching, which is principally founded in more of the formal side, and then added this approximate side through deep learning, and some really interesting things emerge. In this other work that's being led by Guy Katz that we just recently published last month, what we're trying to show is that because neural networks are approximate by nature, if they're used in critical systems, that approximation may not be sufficient. So for example, if we use a neural network to drive an autonomous vehicle, there may be concerns, and probably very justified concerns, about that type of probabilistic or statistically driven nature of the software. But these are, in my mind, two interesting examples of what happens when you take the approximate side of things and you combine it with the precise side of things. It's my sneaking suspicion that as we move forward, we'll see an abundance of more work in this type of area. While we're talking about the different techniques for MP, I want to quickly turn our attention to deep learning for machine programming. One of the questions that I often receive is, when we do this, does this mean it's neural programming? And by neural programming, what I mean is the program is actually solved directly by a neural network, and our traditional form of code is sort of elided away entirely. While I certainly see that there is interesting work that is coming out in this space, there are two examples here. Learning to Optimize, which is iClear 2017, and this zero positive learning approach from NeurIPS 2019. And both of these systems essentially replace code with some form of neural network. Unfortunately, these types of approaches also raise some questions that, while I obviously am support of these types of neural programming systems, as I'm an author on one of those papers, there may be limitations to this type of approach that I think we need to be cognizant of and work toward trying to address. Some of them are listed here. In addition to this, I think that there are other ways to use deep learning in the space of machine programming and not generate a neural program. And one example of that is halide, which I'll talk about a little bit later, and you'll see a concrete example of how you can use deep learning in the space of machine programming, but instead of generating a neural network that's the code, it actually generates code. And the byproduct of that is it may be more understandable, interpretable, debuggable, that type of thing. In addition to that, it may overcome one of the primary challenges, which may be a full retraining of that model if things change. So as we move forward in the space of neural programming, which I do want to emphasize, I think is a very exciting way to explore machine programming, I think we maybe just need to keep our eye on some of these questions and try to understand the implications and maybe try to address some of these things. So now I'd like to move on to the next topic, which is about code semantics. Now, this topic name is a bit of a handful, so let's not focus on the whole thing. Let's just break it apart and start in a more simple fashion. I think one of the first questions I usually ask when someone says I should be interested in something is why? So why should we care about code semantics? It's my belief that the Hoppity work out of iClear 2020 is a great example of how code semantics could potentially help us. If you're not familiar with Hoppity, the high-level synopsis is that it is a system that automatically identifies and fixes bugs in JavaScript. And based on the experimental data they have, it's done a pretty fantastic job. Approximately 10,000 bugs out of 36,000 that they analyzed were identified and correctly fixed. I think that's fantastic. But while I'm a huge fan of this paper, one of the questions I had in my mind while I was reading it is, could Hoppity do better if the semantics were somehow known? What Hoppity does, based on my understanding, is it looks at the change sets in repositories, and as long as those change sets are within some small threshold, it can be flagged as a potential bug fix. And while in many cases that turns out to be correct, it seems clear that that type of approach is sort of a bit nebulous. it would be interesting, I think, if we could do more in the space of automatic extraction of semantics. And doing so, I think, could help systems like this. In addition to that, I also want to give praise to the Hoppity folks in that I think that the way they went about this is actually very clever. And I often wonder if we can do more of this type of approximate type of extraction or inferment of semantics, but we do it in a multimodal way. So rather than just looking at one aspect, we look at it from a multidimensional aspect, and then we use some sort of consensus to tell us, yes, this is a bug fix. So this might also be a possible way forward for extracting out semantics. So now that we understand, I think, why code semantics matter, we can move on to the other two parts about evolving and multidimensional. In my mind, the evolving piece of this is actually pretty trivial to explain. The high-level idea is that if code is used, it tends to be maintained, and code that is maintained usually has changes in its behavior. Those changes in behavior may then alter its semantics. The part that may be a little bit unclear is this multidimensional aspect. So why would we care about multiple semantic meanings for the same code snippet? And with that in mind, I'd like to point our attention to a paper that my colleagues and I from UCLA are working on that's driven by Roshni Iyer. And in this work, what we attempted to do is create a new structural representation called the program-derived semantics graph, which is intended only to lift semantic meaning out of code, with the exception of one layer in the PSG that's used specifically for syntax. And the reason for this is as we move further in the space of things like code similarity, code recommendation, automated code generations, or language-to-language translations, I think that semantics tend to be more important than syntax. So to take a deeper look at the PSG and try to understand why this might matter, what you see in front of you here is an implementation of exponentiation written recursively, and the associated PSG that would be generated from that piece of code. Now, if we look at a second implementation of exponentiation, but then write it iteratively rather than recursively, we generate a slightly different PSG. It's close to the original, but it's not exactly the same. And one of the things that is really exciting about the PSG is it's designed that at the lowest level, it has a syntactical representation. But as you move up the structure, each level increases in the layers of abstraction. And the idea is principally that we may need to analyze code at different semantic levels. And so if we can create a structure that might capture all the different levels of abstraction that we think we might be interested in, then maybe this can be a more general purpose type of system. And to see more concretely what I mean about this is if we look at these two implementations, we can see, okay, they're both implementing exponentiation, only with integers though. They're both correct. One's recursive, one's iterative, and one has more branch paths than the other. What's interesting though is all of those semantics are important in some degree. First of all, the fact that they are correct gives us something that we can use potentially as a baseline to identify bug fixes, or potential bugs that may exist in code, and then we can give suggestions for corrections. On top of that, when we think about recursion and branching, for those of you who are computer architects, I think that you can easily start to think about cases where in an embedded space that has a limited size call stack, if it's recursive, we could blow the call stack. Likewise, if there are too many branch conditions, the speculative execution for branch prediction can become challenging. Now, I know what some of you may be thinking, especially those of you who are in the compiler space, which is, hey, we've been doing this for decades. This is not new. But the part that I think is new is that as we move forward with machine programming and build some of these structures to extract out semantics, I think many of them will require the code to not necessarily be in a compilable state. And one concrete example of that is, as my team was working on doing analysis on C++ code, we started mining GitHub, and what we quickly found out is that most of the repos, as we pulled them and tried to build them, would not build. That left us with millions of repositories for C++ with very few that could actually compile. And so while the compiler folks have done a tremendous job doing these types of analyses, I think that as we move forward, what we will be starting to move toward are things that are more in the space of decompilation. And then the last quick point I'd like to make is, as many of you know, we have lots and lots of code out there. But as the Hoppity folks have clearly demonstrated, there may be very few semantic code labels, and that can create a lot of problems for us. So when taken holistically, I think that trying to identify new and clever ways to extract out code semantics, especially multidimensional and evolving, will be likely important as machine programming moves forward. Which leads us sort of naturally into our next topic, on novel structural representations of code. Again, the first question that I might ask is, why do we care about having new code structures? Don't we have enough? And I think two good examples that demonstrate we might need more are the recent Aroma paper from OOPSLA 2019 and the MISM work that my team, MIT, Georgia Tech, have been working on. While both of these systems are focused in some space around code similarity and code recommendation, both of them claim state-of-the-art performance. But one of the things that's interesting to me about both of these works is that in order to achieve that state-of-the-art performance, they both introduced novel structural representations to achieve that. And in both papers, the authors clearly note that they intentionally move away from an abstract syntax tree to something that is less syntactically driven and more structurally driven. In fact, both the simplified parse tree and the context-aware semantics tree are only one directional. That is, when you take code and you translate it into that structure, you can't actually translate back to code. And this is because what we find with some of these emerging systems, as we start to decompile, oftentimes the machine learning systems that are using and relying on too much syntactic information tend to be confused about the semantics. And you can see concrete evidence of that in the MISM paper, where our system is able to outperform code to vec, which is principally based off of an abstract syntax tree, by up to 40.6x times. So with these two examples, I think that there is some evidence that we need new structural representations, and not necessarily in the space of compilation, but actually in the space of decompilation. I think that we've made some good early progress in these areas, but I believe that there's a lot more to discover. And one of the areas that I think is going to emerge is a new class of structural representations that can only be built through learning. So what I mean by this is, historically, many of the structural representations that I'm aware of, things like the abstract syntax tree, a control flow graph, static single assignment, these things have rules that you follow to then generate the structure. If you think back to the program-derived semantics graph that I was talking about, one of the core challenges that myself and the team have is we don't know how to build this thing. And in fact, when we thought about it a little bit more deeply, what I think we've all realized is we don't believe it can be built by a set of rules, that it's possible the only way to build it is to use something other than a rules-based approach, which might imply some sort of machine learning to infer out semantic information from the code and start to generate those semantic nodes. It's my belief that the PSG is one of potentially an entire new class of structures that will be learned. And I think this actually goes back to the prior point where we segment the field into approximate and precise solutions. I envision that the approximation in this sense is how to take the code and generate the correct nodes and edges for these various structures. But the precise part is the actual structure that then is created and then utilized for things like code similarity, code recommendation, automated bug fixing, and so forth. Okay, so moving on, now we can talk about heterogeneity. As most of you are probably aware, software and hardware is becoming significantly more complex due to heterogeneity. And what I mean by this is that there is a growing number of programming languages, especially when we start to think about things like domain-specific languages, and there's a growing number of classes of hardware. For someone that has been at Intel for the last decade, when I first joined Intel, I can say definitively we were homogeneous. There was really one type of hardware, and that was the CPU. What I've seen over the last few years is we've transformed into a very heterogeneous hardware company, that we are using many different types of hardware for many different purposes: CPUs, GPUs, FPGAs, ASICs, neuromorphic, and hopefully quantum. And there's probably others that I'm missing. So when we have all of this heterogeneity, complexity, how can we manage it? I think that it's unrealistic to think that programmers themselves will be able to handle this complexity. So I believe we need to start automating some of this. And two examples that are moving in this direction are the verified lifting work that's being primarily driven by Alvin Chung and his team, and the halide work that originated from, if I recall correctly, Jonathan Reagan Kelly's PhD dissertation and has led to a flurry of follow-up work. What's interesting about these two systems, in my mind, is if we look at the verified lifting example, this paper called Automatically Translating Image Processing Libraries to Halide, what it's attempting to do is take C++ code, lift it out into a higher level, essentially lambda calculus in the form of domain-specific language, and then translate it into a target language, which in this case is halide. Then once it's translated to halide, because of halide's separation of concern design, it allows it to do some really interesting things as far as automatic optimizations. But this paper, I believe, is a strong demonstration of early work showing that we can do automation for software heterogeneity. The second work on halide is showing, in my mind, a little bit more about the hardware heterogeneity. This is from SIGGRAPH 2016, and for those of you that are on the call that are from the halide team, don't worry, I know about your 2019 paper, and I'll be getting to that shortly. But in this paper, what they show is because of the design of halide, its separation of concerns, which we'll go into a little bit more detail later, they're able to target multiple hardware backends. I believe in this paper, it's principally focused to multiple CPUs and multiple GPUs. But the takeaway is that it's done in a fairly autonomous fashion, that there is some manual coding on the side of the algorithm, but as far as the optimizations, or what they call as the schedule, those are mostly handled automatically by their auto-tuner, auto-scheduler. Another thing that I'd like to quickly point out about both of these works is these, in my mind, are both strong examples of precise solutions. To my understanding, these particular papers don't use machine learning at all. The later work from the Halide team, the 2019 paper, this does use machine learning, but this prior one, if I recall correctly, is principally a rules-based solution. And this sort of goes back to that notion that machine programming can be very precise in nature. Another thing that I'd like to quickly draw our attention to is pushing these ideas further. So Alvin, who I've been working with for the last 3 years as part of Kappa and as part of Maple, I think he's made some really excellent observations with his research. The first is that the value of verified lifting, I think, is enormous. In fact, across Intel, there are probably hundreds of people that are looking at verified lifting in one way or another, simply because of its practical uses. But one of the observations that Alvin made, sorry, Windows is trying to do an update. There we go. Okay. One of the things Alvin observed is that one of the bottlenecks of the prior verified lifting system is one had to manually handcraft these domain-specific languages as you move from new source languages to new target languages. So the MetaLift project, as I understand it, is trying to reduce some of that technical burden so that people that aren't necessarily experts in verified lifting can start to use this for different types of source languages and different target languages. So I think it's really excellent work that's emerging. I'm not entirely sure of the progress, but I think the direction of trying to achieve generality is the right one. With that said, with, of course, my critical eye, I can't help but ask a number of questions. And one of those is, I don't think that language-to-language transfer in and of itself is enough, even if those systems are correct and performant. And the reason for this is I believe that completely autonomous machine programming systems are likely still decades away. If that's true, that would imply that humans then would have to maintain the translated code. If the translated code from a verified lifting system is potentially less maintainable, that might not be such a good thing. So I think we need to be cognizant of these types of quality metrics. I think the emphasis historically for verified lifting has been on correctness and performance, which of course I think are fantastic quality targets. But I think that there are others that I list here, like security and potentially the power footprint, depending on if it's going to run on a mobile device. So I think it's an excellent start, but clearly a lot more work that we can still do. With that, I'd like to move on to the next topic, which is on intentional programming and behaviors. It's my belief that general purpose programming is fundamentally flawed. And the reason why I believe this is I believe that if we go back to the 3 pillars, one of the problems with general purpose programming is it binds together intention, invention, and adaptation all under the same umbrella. And when you do this, what we find is it tends to handicap the machine from exploring other possibilities of invention and adaptation. However, if you generate systems that are intentional by design, that contain only the semantics that you are hoping for the program to achieve, what I believe this does is it allows the machine the freedom to then explore how to invent that program and then how to adapt that program based on the variety of different solutions that may, end solutions that may be applicable for it. And in that context, what we're talking about really is moving toward intentional programming languages and intentional behaviors. The 2 papers that I think are a good start in this direction are the recent work from ICLR 2020 on property signatures, which if you haven't read this paper yet, I strongly recommend it. I think it's really fantastic work. And then also the work by Sarah and Roz on this idea of skip blocks which the beginning of this work allows the programmer to add these annotations, and these annotations are, in my mind, are in a sense trying to capture out the semantics of what they're labeling. Sarah has gone even further with this, and one of the things she's starting to explore is studying more about intentional behaviors. And what I mean by this is she demonstrated to me in person when I was visiting Berkeley last year how the tool that she's building to mine websites can record a user's example, but then rather than focus principally on repeating the example, what her system, in my mind, is actually doing is it's trying to reason about the behavior. What is the actual intention behind that behavior, rather than just doing sort of an arbitrary repetition of what it has seen. Now, of course, there's another big language that is intentional, and that language is Halide. For those of you who are not familiar with the Halide programming language, I have a high-level diagram here that shows this. This is from Andrew Adams et al. And their presentation at SIGGRAPH last year. In a sense, what Halide originally was designed to do, from my perspective, is separate a program into two primary components. One is the algorithm, and the other is the schedule. The idea here, in my mind, is this separation of concerns is very much what we are trying to describe in the three pillars of machine programming, that the algorithm, in this case, is the intention. And the schedule, in this case, is part of the invention, and a lot of it is actually adaptation. And Jonathan and I actually sat down and talked about this at the last Kappa All Hands, and I think that we have sort of a similar view of this. Now, when JRK originally designed this, I believe that the goal was simply to say, look, the person that's a domain expert isn't necessarily a person that has a PhD in computer engineering. So it's sort of unreasonable to believe that one person may have both of these skills. So instead, let's design a language that enables a domain expert to express what their expertise is in that domain. And for those that are experts in software programming and computer architecture, let them work on the optimizations. These are people that we call ninjas at Intel. So that was the original intent, as I understand it, when JRK was creating Halide. But what they observed in Halide as they started to move forward is that the scheduling part, because of this separation of concerns, because the algorithm is intentional by nature, they can then automate the schedule. And the 2016 SIGGRAPH paper represented this to some degree. The 2019 paper took this even further. And for those of you that may be skeptics of this idea of intentional programming, I think the data is showing, at least early evidence, that this can potentially work and work very well. What I'm showing you here is a comparison to the 2016 work that I mentioned earlier, these expert programmers, and then the results that they have from the 2019 paper. When they refer to expert programmers, I think it's really important to understand they're not talking about just sort of the average programmer. They're talking about, as I understood it, like them. They are challenging themselves and other experts in the Halide community to write the most efficient schedule that they can, and the machine is still beating them. And much of this, I believe, is only possible because of that intentional design. With that said, being the skeptic, I think there are questions that we still need to ask. The first is that Halide, as many of you know, is essentially a DSL. The one question that I have for Jonathan and Andrew Adams and Kayvon and the folks that I've been working with is, can we do this generally? I think that this is a very challenging problem. I'm not entirely sure what the answer to that is. The other question that I have is, can we take something like Halide that is intentional by design and provide intentional interfaces to existing widely used programming languages. The idea here is principally that we don't want to move the programmer into an entirely new language, but we want to get the benefits of intentionality in their programming. And so Maz Ahmad, one of Alvin's PhD students, spent a summer with us and built what we call the intentional C++ prototype. And it turns out that things are actually looking pretty promising. So still tons more work to do, but I think there's a number of interesting problems that we can start to tackle now that we have some concrete evidence that this type of approach is leading to quote unquote superhuman performance. And the last topic I'd like to discuss is the future of essentially hardware, or MP. When I think about machine programming, given that I work at Intel, a lot of the questions that myself and my colleagues are wondering about is, what does the hardware look like? So let's say we're successful with machine programming and we're starting to synthesize these really fantastic systems, or it's able to do automatic bug mitigation at scale. What does that look like? And what are the challenges as far as computation and communication and data? As I mentioned before, MP data is large and can be dense. And by dense, what I mean is, unlike other things where you may only be able to look at it one way, code allows us many different purviews that we can look at it from the code itself. We can create structures from that code and look at those structures. We could look at comments. We could look at natural language associated with Stack Overflow. We can do a number of things that are sort of tertiary, such as looking at the repositories that this code lives in, and do things like what the Hoppity team did, was look at change sets. So there's a variety of things that we can look at. And all of the things I mentioned, those are only related to static analysis. They don't even get into things like running the program and looking at traces, execution behaviors, hardware telemetry, that type of thing. So given all of this, what does this future look like? I have no idea. In complete transparency, I really don't know. And I can say that I've thought about this in some depth, and it's not clear to me. But I do have ideas on things we can potentially think about. So some of the things that I've been thinking about are the following. The first is, I think it's probably clear that I'm a big fan of these types of expressing intention. And so what are the ramifications of moving forward with these types of intentional approaches? The other question I have is, what are the different techniques that we'll use, and what are the implications of those techniques? So for example, if we find out that genetic algorithms turn out to be really effective for MP, that might mean that because of the largely parallel and distributed nature of GAs, we can focus on distributed clusters. But if we focus on something else that tends to be a bit more serial, something like long short-term memories, that if you break apart the sequence, they may not be as effective. Those types of things. And then lastly, as I mentioned in the abstract, and as you may have noticed from the 3 pillars, data is a core piece of everything we do in machine programming from my perspective. As of this summer, I noticed that there are over 200 million GitHub repos. And as I mentioned before, code is multidimensional or dense by nature. I believe that the implications of this have a potentially profound impact on the future of the data systems that we are likely to design, and that the current ones we have, it's quite likely, I believe, are not sufficient. So with that, I'd like to just kind of wrap things up. The topics that I wasn't able to cover are these 3. I think all 3 of these are super important areas, but unfortunately, given time constraints, I wasn't able to cover them. If you are an expert in any of these areas, I would strongly encourage you to raise it in the breakout groups. and hopefully we'll be able to have deeper insight than I would possibly be able to arrive at. So in closing, I would like to just share one final thought with you. I believe the era of machine programming is now. As many of you know, I've been working in the space of machine programming nonstop for the last 5 years. I have finally convinced Intel to make a massive pivot in their direction to embrace machine programming. As some of you may know, machine programming now is labeled as a pioneering research effort at Intel Labs, which basically means we're in it for the long haul. And on top of that, we're not just in it with research. We have hundreds of people at Intel working on not only research, but engineering of machine programming systems. And we're not alone. If you look at many of the large tech companies, you'll see almost every single one of them is also looking into this. Being in the Valley, I know that there are dozens of startups that are focusing on this. And as my involvement with a lot of the academics that are on the phone today, I know many of you are working in this space as well. My long-term goal with machine programming is really to democratize the creation of software. I imagine a global population where everyone can express themselves and their creativity. If you look at the numbers that we have right now, 27 million people are able to code out of a global population that's almost 8 billion. That makes us the 1%. I don't want to be the 1%. I want us to be the 100%. And on top of that, I will imagine a world where coders only spent their time expressing their intention, not fixing bugs, not optimizing. And I think we'll be largely more productive if we're able to achieve this and have advances in a number of different ways, some of them scientific, some of them artistic. I think that the sky is sort of the limit. And with that, I would like to say that I hope that I get the chance to work with many of you, maybe all of you. I already am working with some of you, and I'd like to thank you for your time. I'm done.